Welcome back, propeller heads. This is Morgan coming to you, talking about equilibrium constants today. We are on page 5 of the AP lecture outline called equilibrium. So, what is an equilibrium constant? Let me actually describe it to you 3 different ways. It's a ratio. And because it's a ratio, I can also say it's a number, hence the name constant, right? And it is an algebraic equation. Now, none of these actually will violate any of the other descriptions. Okay? They all support each other. It is possible to have an algebraic equation that can be represented as a ratio, and it can be calculated out as a number. Okay? So, what does an equilibrium constant look like? The generic form we will call K, capital K, EQ. The K is not to be confused with the rate constant from the last chapter. And we typically say products over reactants. So the concentration of C to the C, the concentration of D to the D, over the concentration of A to the A, and B to the B. And the square brackets, if you remember, always represent molarities. These are concentrations. Now, because these are based on concentrations that change, we actually only include gases and solutions. Dilute aqueous solutions is the term that we use here. We will not put in solids and liquids, okay? Their concentration is constant. Now, it is possible for us to calculate the molarity of a solid. Say we do it for a rock. If we cut that rock in half, it's still the same ratio, moles per liter. Okay? Now, water. We wouldn't include liquid water because that's pure liquid. Okay? Now, if we add more water to it, are we diluting it? Is it becoming more watery? I don't think so. It's still pure water. Now, if you have a pure liquid and you add some water to it, it ceases to be a pure liquid and it becomes a solution. Okay? So we include gases and solutions. Now, this actually can be traced back to rate laws connected with it. Let's imagine that this is an elementary step, and I can write the rate law for the forward reaction, R forward, equals K forward, the rate constant for the forward reaction, times A to the A and B to the B. And because it's an elementary step, those can just be the stoichiometric coefficients. Now, the rate for the reverse reaction equals K for the reverse reaction times the concentration of C to the C times the concentration of D to the D. Okay? So I have a forward and a reverse reaction. And my definition of equilibrium is when the rates of these two reactions are equal. So rate forward equals rate reverse. And what I can write is that K forward times A to the A and B to the B equals K reverse times C to the C times D to the D. Now if I just rearrange that algebraically, I group like terms, as they say in Algebra 1, K forward over K reverse will equal the concentration of C to the C, D to the D, over A to the A, and B to the B, which looks a lot like K EQ. So essentially, the numeric value of the equilibrium constant equals the rate constant for the forward reaction divided by the rate constant for the reverse reaction. Okay. Now, there are a lot of different Ks. They all take this same basic format, but we give them some special names. KEQ is kind of the generic term. C is for concentrations. P is when we actually do it with pressures. That's the only one that looks a little bit different. Ka for an acid, Kb for a base, Kw for the autoionization of water. KSP is called a solubility product. Kf is a formation. Okay? So, we'll look at samples of a lot of those on the next page here. Okay? Where we're going to be writing some equilibrium constants. So, for this reaction, we have N2O4 divided by NO2 squared. Pretty straightforward. For this second one, we have HI squared over H2 times I2. Don't think this is too hard for you. Then we have SO2 times H2O divided by SO3 times H2. And one more very straightforward, simple one, PCl3 times Cl2 divided by PCl5. Now, let's look at them getting a little more unique. Kc for this reaction. Now, I am going to eliminate this and this because it's a solid and a liquid, and I'm going to have the concentration of O2 gas raised to the sixth divided by the concentration of CO2 gas raised to the sixth. Okay? Number 6 is for an acid. I can get rid of the water. It's a Ka. So I'm going to have concentration of H3O plus times Cn minus divided by HCN. Okay? This is a base. I'll get rid of the water. So I have the concentration of NH4 plus times OH minus divided by NH3. Now, what I can basically say here, no pun intended, is that for whenever I have a Ka, I'm going to have H3O plus right here. And whenever I have a Kb, I'm going to have OH minus. Okay? Because those are the dissociation equations for acids and bases. That's what they produce. Now, Kw is a very special one. It's called the autoionization of water. This is the one and only Kw we're actually going to expect you to remember. It turns out to be 10 to the negative 14. It tells you don't get a whole lot of that stuff in water. Now, this is a solubility product. How much can a compound actually break down? Is it soluble? Ag plus times Cl minus. We ignore the AgCl solid. Now, important point here. We say that AgCl is insoluble, that it doesn't dissociate. So the value for this is actually a very small number on the order of 10 to the negative 10th. Okay? Now, a Kp. That means I put the pressure of AsF3 times the pressure of F2 divided by the pressure of AsF5. That's the only one that looks a little bit different. And since this is actually the formation of a transition metal compound, or a complex ion, some people say it, we call this a K of formation. Ag NH3 sub 2 plus divided by Ag plus times NH3 quantity squared. Okay? So pretty straightforward idea there. Don't think that's going to be too hard for you. We did a lot of that last year. Let's take a look at how to calculate some of these numerically. So the concentration of N2O4 divided by NO2 quantity squared. So here are my concentration values, all molarities, for 3 different experiments. So K for number 1 here would be 0.595 divided by 0.052. That was that number and that number. That's got to be squared. This ends up equaling 220. paying attention to sig figs here. I'm giving it to you as two sig figs. Okay? So for the second one, I've got 0.127 divided by 0.024 quantity squared, which again comes out to be 220. Does that surprise me? No, it's an equilibrium constant. It's showing you the extent to which the reaction happens. And for the third one, I have the 1.02 divided by 0.068 quantity squared. And again, I get 220 when I list it as two sig figs. Okay? Your calculator might give you something a little bit different in that third digit, but remember there's always some uncertainty in the third digit, or in the last digit, sorry. So here, I chose this one specifically because I wanted you to have one that involves a cubed. NH3 quantity squared divided by N2 times H2 quantity cubed. So go and run these through your calculator right now. See how you do. Come back. Check it out. All right, so welcome back. NH3 is 0.157 quantity squared over 0.921 times 0.763, which is cubed, and I got 0.0603 on my calculator. 3 sig figs. The next one, 0.203, which is squared over 0.399 times 1.197 quantity cubed, and I got 0.0602 that time. Uncertainty in the last digit's fine. Then on my last one, 1.82 squared over 2.59 times 2.77 quantity cubed, 0.0602. There you go. Numerically, that's how we just plug in to calculate these. It's an important skill, and it does actually pop up on AP exams. All right, so let's take some time now and actually manipulate some equilibrium constants. So I'm giving you this reaction. I just made this number up. Don't worry about that, okay? Here you go. Here's a reaction. What is the reverse reaction, and what is K? Well, K here equals the concentration of Br squared over the concentration of Br2. So for the reverse reaction, which is 2Br gas comes to equilibrium with Br2 gas, the K equals Br2 over Br quantity squared. Now I'm hoping that what you're going to recognize here is that this is the inverse of this, so that when you write a reverse reaction, the equilibrium constant will now be the inverse of the original equilibrium constant. Now that holds true mathematically also, so the numeric value here would be 1 over 2250. Now for twice the forward reaction, we have 2Br2 gas gives me 4Br gas. My K would equal concentration of Br to the fourth over the concentration of Br2. Now when I look at the relationship between these two, I realize it's K squared. So I take my 2250 and I would square it. Now for half the forward reaction, 1/2 Br2 gas to give me Br gas, the K, is going to equal Br, concentration of Br, divided by Br2, raised to the 1/2 power. Well, when I compare these two values right here, I'm getting a square root. The square root of 2250. So, anytime you reverse the reaction, it's the reciprocal of the K. Multiply the reaction by 2, you square it. Multiply it by 1/2, you raise it to the 1/2 power, which we call the square root. Okay. Now, question 2 here, we're going to manipulate this value of K. I kept it to a, this number's fake, don't think this is real. but I'm doing this with the mathematics CZ. Here's this reaction, which really happens according to this K. So what's the value of K for this reaction? Well, it's the inverse, because that's the reverse reaction. 1 over 100, but I would typically write that as 0.01, or I would write it as 10 to the negative 2. Now for B here, okay, that is 1 over 100, which will be squared, which equals 10 to the negative 4th. This one is the reverse in the square root, so 1 divided by the square root of 100, okay, which equals 0.10, or we could say 10 to the negative 1. Here it's 100 squared, which would be 10 to the 4th, and for the next one, 100 cubed, which is 10 to the 6th, because here I doubled the reaction and here I tripled it. Okay, these make great multiple choice questions. So now we have to consider if we have a system of 2 equations, okay, and what's going on here. Well, when you add 2 equations together, you multiply their KEQs. So here in this one, I want this first equation, 2 BrCl gas gives me Br2 gas and Cl2 gas. I don't want to change it at all. K equals 0.45. But I want to reverse this one to get the I2 over there. So I2 gas plus Br2 gas gives me 2 IBr gas. And this K is going to equal 1 over 20, or 0.05. So when I go and I add these together, the Br2's cancel. And I get my 2 BrCl gas plus my I2 gas to give me my Cl2 gas plus 2 IBr gas. And the K is going to equal these two multiplied together. So 0.45 times 0.05, and that equals 0.025. So when you add equations together, you multiply the K's. Okay, so that's a nice little trip through how we deal with writing equilibrium constants. And in our next video, we're going to get into the much more complicated equilibrium situations. Okay, thanks for tuning in. This is Morgan, and I am signing off.